In this video, we'll discuss subspaces of vector spaces. So in many situations, it's useful to view a vector space as some subspace that's part of a larger space. In these situations, the subspace inherits all of the properties of the larger space, while sometimes carrying additional properties. An example of this would be that the space of differentiable functions is a subspace of all continuous functions. So a differentiable function, as we know from calculus, is continuous, while also having the property of having a derivative. So a subspace of some vector space is just some subset that also satisfies all of the conditions for the vector space. However, instead of verifying if that subset satisfies all of the 10 axioms that we've listed previously, it's enough to just check the closure properties. Right? So we just need to check that the subset is closed under addition and also closed under scalar multiplication. Sometimes an additional condition is added to these two because this condition is very easy to verify, right? So the extra condition is that the subset has to contain the zero vector for it to be a subspace. The reason we add this additional condition is that it's very easy to check if W contains the zero vector. However, it's not necessary. This condition isn't necessary, right? Because from property 2, if you take C to be 0, then 0 times any vector is the zero vector, right? So the fact that a subspace contains the zero vector follows from condition 2. So two simple examples of subspaces for any vector space is the zero subspace and the vector space itself. Right? So the zero subspace is just the vector space that only contains the zero vector. And this is always a subspace, right? Because the zero vector added to itself is always the zero vector, because it only contains the zero vector, so that's the only thing you can add. And any scalar times the zero vector always gives you the zero vector. So the zero subspace satisfies the two conditions, and the vector space itself is obviously a vector space, and so any vector space is always a subspace of itself. However, these two subspaces usually aren't that interesting. So typically we're interested in subspaces other than these two, right? So somewhere in between the zero subspace, so bigger than the zero subspace but smaller than the vector space itself. These are called proper subspaces. So in the rest of this video, we're basically just going to look at examples where the subset is either is a subspace or not a subspace. So in general, to prove that a subset is not a subspace, it's typically enough to just give some example vectors that fails conditions 0, 1, or 2. However, to prove that a subset is a subspace, you need to show that conditions 1 and 2 hold for all vectors in W, and not just any particular example. Okay, so let's look at the first example. In this example, the claim is that the subset of symmetric matrices is a subspace of all n by n matrices. So here it's going to be helpful to describe this subset using set builder notation, right? So if you remember, a matrix is symmetric if it satisfies the condition that A transpose is equal to A. Okay, so we can write W in this way, right? So when we use set builder notation, usually there's two parts, right? So on the left, we describe what a general vector looks like. Right? So typically a vector is going to be an n by n matrix, right? So here this notation just says that some generic matrix A is an n by n matrix. And then on the right, we typically describe the defining property to be what this subset means, right? So here we want symmetric matrices. So the condition for a symmetric matrix is that A transpose is equal to itself. Okay, so as we said before, to prove that some subset is a subspace, we have to verify both conditions 1 and 2 for all matrices and not any specific example, right? So we do that by starting with two arbitrary matrices in W and show that the sum of those two matrices also has the defining property. Okay, so let's proceed with verifying condition 1. Right, so again, we start with two arbitrary matrices in W. So we use variables to denote them because they're not any specific matrices. Right, so let's call them A and B. So let A and B be two matrices in W. Right, so because A and B in particular are in W, they have to satisfy the defining property. So we have that A transpose is equal to A and B transpose is equal to B, right? Because they both have to be symmetric. Okay, so now we want to show that the sum is also symmetric, right? So so what about A plus B transpose? So A plus B transpose. So one property of the transpose is that the transpose of the sum of two matrices is the same as the sum of the transposes. Right, so this is the same thing as A transpose plus B transpose. Right, so this, if you go back to chapter 2, section 2.2 on the properties of matrices. Right, so in theorem 2.6, this is exactly property 2. Right, so the transpose of a sum is the sum of the transposes. Okay, so this just follows from that property. Right, so this was from theorem 2.6, property 2, in section 2.2. Okay, so now what do we know about A transpose and B transpose? Well, we know that they're symmetric, right? So that means that they satisfy this property, right? So A transpose has to be the same as A because it's symmetric, and B transpose has to be the same as B because it's symmetric. Right, so this is just from this property here. But then this shows that this shows the closure property, right? So A plus B transpose is equal to A plus B, so that means that A plus B is symmetric. And so condition 1 is satisfied. Okay, so so now let's check condition 2. So it follows along a similar procedure, right? So for condition 2, it's scalar multiplication, so we need a scalar. So a scalar in this case is just any real number, and we need any generic matrix. So let's call it A again. Okay, so since A is symmetric, that means that A transpose is equal to A. Okay, so now we have to verify that it's closed under scalar multiplication, right? So we need to show that C times A is symmetric. Okay, so what does that mean? Well, let's look at C times A transpose. Right, so the transpose doesn't affect the scalar multiple. Right, so this is just C times A transpose, like this. Right, so this is again from section 2.2. Right, so this is now property 3. Okay, and now just like before, A transpose is just the same as A. Right, so this is from here. And so this shows that C times A is symmetric, and so condition 2 is satisfied. Okay, so C times A is also in W, and condition 2 is satisfied. Okay, so basically this is the general procedure to verify the two conditions, right? So you start with arbitrary vectors. In this case, they're matrices, and you have to verify. So for condition 1, you verify that the sum of those two matrices satisfies the defining property, and for condition 2, you check if the scalar multiple satisfies the defining property, whatever that is. Okay, so now in example 2, we're looking at the subset of R3, and the defining property in this case is that the three coordinates x, y, and z have to satisfy the equation x plus 2y minus 3z is equal to 0. If you're familiar with equations like this, geometrically, this just defines a plane in three-dimensional space that passes through the origin. Okay, so let's verify. So the claim is that this subset is a subspace, right? So we need to verify the two conditions. So condition 1 again is that it's closed under vector addition, right? So again, we start with two arbitrary vectors. So let's call them u and v. So u. So let's say the coordinates are x1, y1, and z1. So say this is in w, and v. Let's call the coordinates x2, y2, and z2. So we take two vectors in w. Okay, so what does it mean to be in this subset, right? So that means that the vector has to satisfy this property. So x1, y1, and z1 satisfies this. And x2, y2, z2 also satisfies this. Okay, so for condition 1, we're interested in looking at vector addition, right? So what happens to u plus v? Well, let's just do the calculation, right? So what is u plus v? Well, it's just adding the two vectors together, right? So you can write as x1 plus y1, comma, sorry, the x1 will be x1 plus x2, the y1 will be y1 plus y2, and the z1 will be z1 plus z2. Right, so these are the x, y, and z coordinates of the sum. And okay, so now we have to show that the sum is also in W, right? So that means that it has to satisfy the defining property, and so the three coordinates should satisfy this equation, right? So let's check. So we have to add the coordinates in this way, right? So x1 is the x coordinate, x1 plus x2 plus 2 times the y coordinate, which is y1 plus y2, minus 3 times the z coordinate, which is z1 plus z2. Okay, so what is this thing equal to? Well, let's separate the components, right? So this is just x1 plus 2y1 minus 3z1 plus x2 plus 2y2 minus 3z2, right? So this, and this. And then, however, this is coming from this equation, so this part is equal to 0. And this is coming from this equation, so this part is equal to 0. So this is 0 plus 0. Right, so that's just from these two equations here. And so this shows that this, so that these three coordinates satisfy this equation. And so u plus v is also in W. Okay, so that shows condition 1. And then again, condition 2 is similar, except now we do scalar multiplication, right? So let's write it out, right? So we first take a scalar and an arbitrary vector, x1, y1, z1. So again, it satisfies the property, right? So this means x1 plus 2 y1 minus 3z1 is equal to 0. Right, so the defining property. And then now we check scalar multiplication. So c times u is just multiplying all the components. And now we check the equation, right? So what is cx1 plus 2c y1 minus 3c z1? Well, c is a common factor, so I can factor that out. And then this is just the same as this, right? So that this part is equal to 0. But anything times 0 is equal to 0. Right, so this shows that the scalar multiple is also in W. Okay, so this shows the closure property, and so condition 2 is done. Okay, so in general, all the subspaces in the plane or in three-dimensional space are not too difficult to describe. Right, so as before, the zero subspace is always a subspace, and the space itself is always a subspace. However, in terms of proper subspaces, for the plane, the only proper subspaces are the different lines that pass through the origin. And for three-dimensional space, the only proper subspaces are either lines passing through the origin or planes passing through the origin. In this case, the zero vector should have 3 components. Okay, so we looked at some examples of things that are subspaces. What about what happens when something is not a subspace? So let's look at some of these examples. Okay, so the first example here is the set of singular matrices, right? So the claim is that the set of matrices that are not invertible does not form a subspace. Right, so if you remember, singular we can tell if something is invertible or not invertible from the determinant, right? So singular means that the determinant is equal to 0, and non-singular, meaning invertible, means that the determinant is non-zero. Okay, so for a 2x2 matrix, the determinant is just AD minus BC. So the fact that it's not invertible means that AD minus BC is equal to 0. So that's the defining property. Okay, so we want to show that it's not a subspace. So so we need to show that it either violates condition 1 or condition 2. So in this case, it's going to violate condition 1, right? So we want to show that it it's not closed under vector addition, right? So what does that mean? We need to find two matrices that satisfy this, but then the sum does not satisfy this, right? So need to find two matrices right, so this is the defining property. So that satisfy the defining property. But the sum does not. Okay, so in this example, we can take, say, A to be this matrix and B to be this matrix. Right, so you can see that determinant of A is 0, right, because it's 0 minus 0, and this is also 0 minus 0. Right, so both of these are singular. However, what about A plus B? So A plus B would be this matrix, and the determinant of this matrix is 1. Okay, so condition 1 fails. Okay, so let's take a look at the next example. So the next example basically says that the set of invertible matrices is also not a subspace. Okay, so let's take a look at this, right? So as we said, invertible is the same thing as non-singular, right? So is where the determinant is not equal to 0. Well, if for a matrix to be invertible, the determinant has to not equal to 0, right? So that means that the 0 matrix is not invertible. So condition 0 fails. Okay, what about condition 1? Well, automatically it's now automatically not a subspace, right? Because it already fails one of the conditions. But you can see that it also fails condition 1, right? Because say I take the identity matrix, right? So this is invertible, and minus the identity matrix. This is also invertible, right? Because these determinants are 1. But if I add them together, this is the 0 matrix, which is not invertible. So condition 1 also fails. Okay, so all the conditions fail for this subset. Okay, so let's take a look at the last example, where we have this subset of R3, where the x, y, and z coordinates has to satisfy the equation x squared plus y squared is equal to z squared. So the claim that this is not a subspace of R3. Okay, so let's first take a look at condition 1. So in a lot of these kinds of examples, what you might want to do is to play around with different examples and do the calculations to get a feel for whether one of the conditions is satisfied or not. Right, so it's not always obvious just from looking at it whether the condition should be satisfied or not. But in this case, condition 1 is not satisfied. Right, because let's try to find some examples. Right, so this just looks like the Pythagorean theorem, right? So we just need to pick points that satisfy the Pythagorean theorem, right? So let's say 3, 4, 5. Right, because 3 squared plus 4 squared. So that this is equal to 25, which is equal to 5 squared. Right, and let's pick another one. So 5, 12, 13. Right, because if you do 5 squared plus 12 squared, this is 169, which is equal to 13 squared. Okay, so now we check the sum of this. Right, so let's call this u, let's call this v. Right, so what about u plus v? Right, so 3 plus 5 is 8, 4 plus 12 is 16, and then 5 plus 13 is 18. Right, so now we have to check this equation for this, right? So we check 8 squared plus 16 squared. What is this? This is 64. (16 squared) is 256. What is that? 64 plus 256 is 320. What is 18 squared? Should be 324. Right, so this is not equal to 18 squared. Okay, so condition 1 fails. What about condition 2? Well, if you think about it, right, so what is condition 2? It's scalar multiplication, right? So if I multiply all of these by c, what happens to this equation here? So you get c squared coming from this term, and then c squared coming from this term, and then an extra c squared here. But if you have c squared and c squared, then you can factor that out. So condition 2 should be satisfied, right? So let's check it. So c is any real number, and x, y, and z is in W. So x squared plus y squared is equal to z squared. So this is u. So now c times u is cx, cy, cz. Right, but now if I write out the equation for this, right, so I can just factor out the c squared. So you get c squared x squared plus c squared y squared is equal to c squared z squared. So we start with the left side, right? So c x squared plus c y squared, and then I can factor out the c squared times x squared plus y squared. But then, okay, so now x squared plus y squared is equal to z squared from here. Okay, but then this is just c times z squared. So condition 2 is satisfied.